Edgar, just twist one of those so I get a little bit of sunlight. It's a little bit too dark.
Sorry, that really hurts my eyes when the lights off.
Thank you.
I have to get over that? That's what you're going to tell me if my eyesight's so bad?
Yeah.
You need a little bit of light. When your eyes, when it's too dark in that, that's actually going to hurt your eyes more.
But it hurts. I come out of this class with like a headache all the time because the light.
Because the lights are off like that.
No.
Let's open all the lights. You open all the lights?
Me, Mr. Howell.
Try now. Okay. You really shouldn't be looking at your notes with no light on at all. That's what I'm saying. All right, so area between two curves. So imagine I have some function f of x and some function g of x. And I'm starting in a way that's different than what you see in a lot of books. And I'll give you the reason why in a minute. And I really think it'll help. And this is kind of the way I learned it when I thought about it. A lot of books put both of the curves above the x-axis to start. And I'm not going to do that to start. And you'll see why in a minute. So, if I asked you, Kerry, if I wanted to know the area between these two curves, okay, that's my ultimate goal, to find that entire area that's enclosed. So I want to know what the area is pretty much between the line x equals 0, the line x equals whatever this may be, let's say for this case c. Okay, if I want to know the area between x equals 0, x equals c, g of x as another one of my regions, and f of x as the other region. So the four dashed lines where those intersect, that odd looking shape in here, I want the area of the whole thing. Okay, that's my quest for today. Which one, Kerry? And I'm asking you for a reason. You probably know why already.
The integral from 0 to c f of x.
Good. That's the upper half. Thank you. Integral from 0 to c of f of x dx. Continue, Kerry.
Plus the integral of 0 to c.
Carrie.
Kerry, entering.
0 to c g of x.
Okay. So when I take the integral though of g of x, what is the answer going to have on it? A negative sign, right?
You're adding it.
But I want the overall area, so what should I do actually? So tell me what to do then, Christian. Okay, that's one way of doing it, very creative. Or what could I just put instead?
Right.
Either that or...
Square.
So if I just do this, watch, let's say I do this. Okay, this is what we were talking about. But the problem with this right now is that this is a negative quantity, isn't it? But I'm asking for the area. I'm asking for the area. So this quantity on the right here is negative. I can't have a negative area. Again, theoretically we talk about areas as negatives when we're looking at integrals, but I actually want the geometric area, the actual area of this space. I can't have this being a negative, right?
Yes, you disregard it because you know what you're trying to do.
So what do you mean disregard it? How can I show that, Christian?
I don't.
What should I do? Just subtract them.
What do you
Take
do
the
that
up.
above?
Just watch. Okay, so we'll talk about that in a sec, and you'll see how we can make a conjecture. Whichever one is above is going to be the positive area, right? Whichever one below is technically the negative area. So no matter what, it's always going to be the lower one below. We can actually make this conjecture and raise it above, and it still works. That's the cool part. And I'll explain that in a sec.
That's why
And a lot of teachers teach it the other way around. They teach that first. But I want to show you guys where, hey, if I just want the area in general, let's just make this a negative sign. Because this area is definitely negative. This blue, and I've shaded blue here just so you can all see, that blue area is really, a negative integral. So as Jocelyn said, if we negate that, or even as Christian said a minute ago, we could have just switched the limits also. But I'm going to avoid switching limits for a reason. You'll see why. For now, let's avoid switching limits unless we really have to. So we'll put the negative there, and now we've got it. Okay? So again, if I want the area between these two, if this upper area were 10, or the upper integral were 10, and the lower integral were negative 15, it would be 10 for the upper, and then you get the minus the negative 15, giving a total actual area of 25. Again, I'm asking, and the test is always going to ask you, when they say find the area between two curves, they want the geometric area. So there is no such thing as a negative area anymore. Okay? Again, whenever anything would have taken on a negative value, we need to have a negative sign. Well, we can generalize and just say that the upper function has a positive, the lower one has a negative, and it will always work. Again, this works if f of x is greater than g of x on the interval 0 to c in this case, which your book will call a to b, and other places will say a to b, and that's fine. But I want you guys to see that a to b are just dummy variables. They're just random locations. So why can't I just say 0 and c? It has no effect on it. But you have to understand that, calculus, you don't have to follow the same rule every time. Call something e and f, it doesn't matter. So here I'm saying 0 to c, and f of x is greater than g of x. Now, let's try to actually apply this to what happens if they're both above the axis now. Okay? And let's discuss why. Okay, let's discuss why. So, draw yourself just the first quadrant. Let's draw a function f of x. Let's draw a function g of x. And let's say we're going from now, let's say we're going from a to b. Just to show you that it doesn't really matter. Let's go from a to b. Okay? So let's say the lower curve happened to be exponential decay. See that coming in? And it really shouldn't lose, it should not gain slope again. It should not really gain slope. Assume it's a exponential decay function. Let's say this is just some sort of a sine function or sinusoidal wave, some cyclic wave coming through. Now, we want to know what is the area between those curves. So, if I wanted to know, again, this region, right here, what conjecture or what idea can we make from this? How do I find the area of only part of a sector, part of a region? Think back to geometry. Yes, take the whole and subtract the part that's missing. Right? So the whole area, take a look at what I'm highlighting in blue. That's really the whole area. And if I could subtract this lower area, I get what's left over. Again, take the blue area, subtract the green area. Okay? Take the blue area, subtract the green area, and we'll get that black area that's left over in the middle there. Okay? Sorry, thank you, Edgar. Edgar, thank you. You're absolutely right. Edgar's right. What did I say? I said we're going A to B, and I went from 0 to C. Thank you for correcting me. But you know what? If you can pick up on that right away, it means that you do understand what I'm saying right now, which is a good thing. Okay? Again, so we want to find the area only in that region. So if we look at this and we say the upper one was f of x and the lower one was g of x, okay? So we got f and g.
Wait, he attached
I know, I switched them after. Did you see that? I realized that too. So if I want the whole area, the one that was in blue, in blue originally, what is that the integral of, the one in blue? F of x. Again, let's take a look and think about this. This blue region that you see, that I'm highlighting right now, that blue region, it is just the integral of f of x from a to b. What is the area of the green region down here? It's just g of x. This area right here is the integral of g of x. So again, what are we doing? We're doing the integral of f of x dx minus the integral of g of x dx. The same exact thing, but this time a to b or 0 to c, doesn't matter, either way. So the idea here, the cool part is that we took an idea where it was negative and used it right, and then it actually applies this way as well.
Would we keep it so as you know how when you find the total area of both, you don't subtract them, right? You add them.
What do you mean? I want the black shaded in area. So I'm taking the
okay,
overall blue one and drop it off the green piece.
You have to join both areas.
Okay. All right. So now the next question becomes this, and we'll get to examples in a minute, but I'd rather do all the theory first. Go ahead. Sorry.
So, flipping the signs will revert to both the x-axis. Maybe make positive. Or I mean, like
No, it actually do the same thing. If you made this a plus, and you made that beta A, exact same effect actually. But the reason you can't, the reason you don't want to do that is what I'm about to do right now actually. So hold that question, that thought, and then think about it after this. All right. So let's say now this is where it gets tough. We got an x and y axis. I want somebody to come up and draw a random function. Come up and draw a random function. Just one. So go
Absolute
from
value, go for
a
absolute
gram, and
value.
you can make it whatever you want to
I
look.
want to do absolute value.
Because it's fun.
Can it cross the x-axis or no?
I said you just draw a function. Okay, good. Even though that's really not, be careful for your functionality.
Yeah, because I know.
Kind of
but-
this is vertical line test would fail.
Yeah.
Mm,
I know. I was just,
I know you're trying to.
It's fine, it's fine. I'm just saying, be careful.
Yeah.
Okay?
Yeah, I know, but not on the scale, so.
Anybody else want to draw another one? I need one more. Now, I'm going to give you one criteria, okay? The function you're about to draw cannot exceed 3/4 of the height of this function at any point in time. The max height of this function, 3/4 of that, this new function you're drawing, cannot exceed that value.
Quarters of the height, right?
3/4 of the height.
So it can only go a quarter, so you can only go like up to there.
So start, if you want to start back here, draw something that does not exceed 3/4 of the height of that function.
Josh, I think it's not complicated.
Okay, perfect. Thank you. Just messing with you a little bit here.
That's a little too high, isn't it?
I'd say it's about 3/4. The max height is here. He did about 3/4. If you cut it, that's definitely, I'd say it's actually closer to 2/3. So, now here's my question for you guys. If I would like, Christian, do you mind if I just extend your function this way a tiny bit? Thank you. If I would like to know,
Is that horizontal or no?
okay, if I would like to know the area between these two curves from A to B. Okay, the area between the curves. So I can see clearly,
No?
here's the lower curve, right? See the lower curve, the black one here? And this red is the upper. So the area between those curves is that. Then once they intersect, now the red one is what? See this red one?
Yeah.
Isn't it lower now? And this is upper? So now isn't that the area between the curves actually? Think about this for a second. I know it's weird.
Yeah.
Here, this is the lower curve, this is the upper, the area between is upper and lower. This is now the lower, this is now the upper. Why did they switch upper and lower?
Yeah.
Because they intersected. So what kind of a conjecture can you make now? What do we have to do when we have functions that intersect? Okay, I'm not saying, I don't know the overall answer, but what do we have to do to like the areas? What?
Sections?
Sections, what is that called? What are we doing to a function now?
Piecewise?
Piecewise, very good.
So the
We make
word
it a
we use.
piecewise function or a piecewise
What is the
integral.
word we use?
What's the other word with a P also?
That's the word.
It's not piecewise.
Partition.
And there it is. I was going to think of a hard drive. What do you do to separate or allocate space? You make a partition, don't you? Partition is a separation. So you're partitioning the function. You find the integral here and then there. So let's go ahead and say this together. Let's say that the red line is F. Actually, let me just make it coded.
That sounds like a tree.
The red line or red curve, sorry, red function is F. The black function there is G. They can't both be F.
What if train line?
Now I want you guys to think, can somebody tell me if I wanted the overall area, okay, the overall area from A to B, what would my formula now be? And I want you to really think about it first. Write it down. Try it first. Here's what I want you to do. Tell me the area from here to here. Call this intersection point what?
See?
Thank you. Call this C on your graph. Call the intersection C. Now find the area from A to C on your own, then from C to B. Okay? And then think about what that means. Find the areas. I'm asking you to write them down. Write down the areas of that first section and the second section, giving those bounds, or given those bounds. Yes. part, anybody? First part? So I want to know this, we'll call this area 1.
A to Z.
Okay, area 1.
Integral of f of x dx from A to Z.
Minus.
One person, please. Christian, continue.
Minus the integral of gx dx from A to Z.
Good job. I wouldn't have to anyway.
So again, the first area, what is the upper function? The upper function is f, the lower function is g. You take the integral from a to c, because we're only going up to here, of the upper function minus the lower function. Okay? Now, eventually, what are we going to do here? We're going to say to ourselves, do I need separate integrals? What are my laws of integration? Remember, the plus sign and the minus sign really have no effect there. So I could write this as one single integral from a to c of f of x minus, f of x minus g of x dx, like that. This is the same thing. And this is our conclusion that we're going to really make here, okay, for the first part. Again, simply because there's no need to do two separate integrals. A plus sign has no effect on it. You could always do that. So if f of x were like x squared, hypothetically, well, let's see, what are we looking at here? It's not x squared, clearly. F of x maybe in that region were some constant function, like 2. You would put a 2 in there. And g of x were maybe a parabola, x squared, or 2x squared, because it's a little steep. 2x squared. So it would be 2 minus 2x squared, whatever the functions are in those pieces. And we'll do examples of that.
Why would it be a parabola? Like, when you say function, are you talking about the function in that specific place?
In that little piece. Imagine nothing else were there, Christian. And you had that little thing. That's kind of a parabola, isn't it?
But a little more expanded.
And it's but see, if you don't know, I'm just hypothetically saying it. If it were a parabola, it might be 2x squared plus 0.1. Or maybe it'll be exponential growth, e to the x. Absolutely. But again, I'm just hypothetical. And I said this, like, this isn't even really constant. If it had done this, and then this, then it would have been more of a constant function. I was, again, approximating, a model. Okay?
In the AP test, they're asking you something on this subject.
You'll be given the functions.
You'll be given the partition functions.
You'll be given like, and we'll do an example in a minute. You'll be given like a sine curve, okay? And then maybe like another curve that goes through it twice, and you use the two function definitions. We'll do examples. We're just hypothetical right now.
Yeah.
Yeah, that was hypothetical. That's the first area. What about the second area over here? Jocelyn, the second area. What do you think for this one? And my limits are what? Where is it? C to B, good.
Just a little
bit of help there,
Oh,
good.
right.
Okay, again, C is the lower limit, B is the upper limit. Okay? All right, very good. Now, as one integral. So we did that earlier like that, and now as one integral, let's write it. So as one integral, we say just the integral from C to B of g of x minus f of x dx. And there's our second area. Again, as one integral, we write it. All right, so what we're going to do now is just do a few examples together and go through it. If you have questions along the way, please stop me. But the idea of where this comes from is a very basic idea because you can see it. And that's why it makes this topic easier. Whenever you can actually visualize something, you really get to make it a lot easier for you. Okay? So let's pick some functions. All right, somebody give me a... no, I want a, let's see, an exponential function.
EX plus 2.
E to the x plus 2, you mean?
Yes.
Okay. Not e to the
Oh,
x.
sorry, yeah.
Gotcha. So we'll say g of x is equal e to the x. Is it plus 2 in the
Yeah, the
exponent?
exponent.
Okay. Works for me.
Minus 5, because it's translated.
Because it's translated. What about an f of x? Give me a function that is linear, right? With a positive y-intercept and a negative slope. Positive y-intercept and a negative slope. Negative 2/3 or? Gotcha. Awesome. All right. Works for me. Okay. So in this problem, let's say for ourselves, we want to find the area between these curves from, I don't know, let's say from 0 all the way to 10. Okay, we want to find the area between these curves from 0 to 10. First thing we have to do. If you're not given a calculator, you got to know which is the upper limit, which is the lower limit, and when do they intersect each other, right?
You have to know how the graphs look.
Hey, when do they actually intersect each
Yeah,
other?
find where they intersect.
Let's look at this one for the first one as a calculator, because this will definitely, yeah, this will be a calculator example. And there's a reason why, and I'll explain as we go through it. So let's take our calculators out and let's graph them. We're graphing from where to where? And what you should really do, please change your picture of your graph. Make one like a dashed line and make one a solid line. If you don't know how to do that, just watch me and I'll do it with you. Sorry, g of x is e to the quantity x plus 2. Notice how I said that? Okay, use the terminology. And the second function was negative 3/2 x plus 4. Guys, I'm going to do, can we all do it in the same order, please? Because I'm going to show you how to do this in the calculator using y1s and y2s, and let's not do it backwards. So make the first one second e, that's the e to the x, second natural log. Make it x plus 2. And let's make the second function, parentheses, negative 3/2. Whoops. Yes. Was it plus 4, Jasmine?
Wait, 3 divided by...
Oh man, this math's gonna be crazy. Okay.
3 divided by 2, you said?
We
Say
could
again?
change it.
No, that's all right. We'll make it work.
What was the graph
I'll
again?
show you that you can make all this
Oh,
work.
no, I see it.
You got it? It's on there, yeah.
Yeah,
All right.
it didn't show until it's done.
So clearly, guys, which one's going to be the higher function from 0 to 10?
Exponential.
The exponential one, right? I mean, come on. It's really going all the way off the graph. So what maybe we should do is this. If we want to, we could do it two ways. First, we could change our window settings to see how high it goes up, right? So what kind of values do we have? We want to know what is the value of the function at, like, say, like 7 or 8. So let's go to our table and plug in 7 and look at the exponential function. It's at 8,000. See that? So let's make our y max like 10,000 so we can at least see something. So let's go to window and just go to our y max and make it 10,000. Okay, leave the y minute, whatever it is. Who cares? That's negligible now. Now let's take a look at this graph. And we can see the exponential function. Well, where's the other function? It's below the graph. Okay? We'll figure out what this point is and we'll pick up y min after. What about over here? Does this actually matter? Doesn't really matter, right, on this side? Why does that matter? Not in the interval. Very good. The interval is 0 to 10. 0 to 10. That's this range here, or this domain here. So let's now go. Let's look at our table. What number should I really plug in for x to see what my y max and min will be? What number? 10. Let's all plug in 10. Jocelyn, explain to the class why you chose 10. The interval ends at 10. And where's the maximum value? Where's the global max going to be from 0 to 10? At 10. And for the linear function, where's the global min going to be? The global min for the negative function, the linear function. Where's the global min going to be? At 10. So here's your global min. Here's your global max. Think about this, guys. From 0 to 10, look at our graph here. The global max will be whatever the function is at 10. The global min will be the min of this function. So we're getting our y min and y max. So let's make this our y max. What number is that? 165,000 we'll pick, because that'll be covering it, right? And we'll pick here, negative 12. So let's go ahead and do that. Let's go to our window. Our x min, we'll change that to 0 again, because we don't care about anything else. Our y min is negative, we said 12. And our y max, 165,000. Now, clearly, what can we see is the problem with functions like this? What's going to happen? Yeah, I mean, like, this function gets way too large to the point where you wouldn't even be able to see the linear function. It's down there, but you can't see it. Because this is only, what, 13 units? And this is how many units, guys? 165,000. So it's not going to be zoomed in like that. But the idea now is that we have to be able to do this for all of our graphs. So let's now look at a function that might work a little bit better for us. So let's say we're looking at the function x squared, or let's say 0.5x squared. Okay, 0.5x squared. And the same one we just had, sorry. And we're going from, and let's just zoom 6 it. Zoom 6 it to go back to standard. Okay, zoom 6 it, please. Now it looks a lot better. Okay, now it's a little bit easier here. Now, if I really want to...
Okay, put their phones out.
It wasn't meant to be any, Christian.
If we're going to do a problem, and say you were the teacher and you wanted to think of a problem here, what would you make your lower and upper limits? What would you ask the person to calculate the area between? Would you do 0 to 10 again for this problem?
No, 0.
No, I wouldn't do 0 to 10, would you?
No, negative 4.
Okay, negative 4, so maybe over here, that's fine. So the area from here to where?
What a negative 5? To 4.
Okay, yeah, I would probably pick another number like 4 because I can see that I have the switch. We agree?
Yes.
That's how I make the problems up. So when you guys are practicing, you could do the exact same thing I'm doing. There is no reason you can't practice and make your own problems. Not to mention all the problems that are in your textbook. Okay? Again, make your own stuff up if you want to. So, in the beginning here, what did I ask you guys to do with the two functions? Make them different, right? And I didn't do it, of course. Let's go over here, and I'm going to change y2. I'm going to make y2 a thick line. So the linear function is now the thicker line. I go back to my graph. I'm going to look at my graph. I'm going to say, all right, there it goes. Now, what did we say again? We said we were going from negative 4 to 4? Where's the intersection here? About.
2.
About 2, right? For the x-axis?
We can check it.
Does the y value matter? Nobody cares. Just the x-axis. Because we're looking at breaking up our limits. The y value has no significance. All we know is that one is bigger than the other. So, we call this y1. We call this y2.
Yeah.
We all agree with that? So, tell me together, please. From negative 4 up until some point, and then we'll go from that point, we'll call it C for now, and we'll go from that point C up until positive 4. From negative 4 to C, whatever that C turns out to be, what is the area between those curves? Between those two curves. I want to know the area up until the intersection point. That's what I'm saying here on the left. That's that part. And the blue part here on the right that I'm asking for, I want to know the area. There's the 4 right here.
Isn't it, isn't it a y squared?
I want that area right there. Okay, I might have gone too far. Let's see. 1, 2, 3, 4. No, it's pretty much right there.
Okay, so it's
Give me one, Kenny guy. Give me the first one on the left.
the integral y squared. No, I was saying y squared because of the other function.
Y squared.
Which one's on top?
Y2.
Y2. Thank you. Not y squared. Subscript.
I'm sorry, y2.
XY.
It's a y. Sorry. My y's are terrible. I'm trying to make capital y's, guys. Is that better?
Yeah.
Y2.
No, y2.
Oh, jeez. Thank you. Okay.
Minus y1 at dx.
Good.
And from negative 4 to c.
Whatever C happens to be at the intersection. Awesome. Okay, again, whatever's on top. Now what happens on the other side? Just switch them. There's one minus the other. So, if you can find the intersection point, and this is a calculator problem, you could do it all right in the calculator. I could type that in, literally. I could type FINT, y2 minus y1, comma x, comma negative 4, comma whatever the upper limit is, enter. It'll give me the area. Do it right on the home screen. Okay, just like we did yesterday, and I'll do it now. But let's find that intersection point first.
I was wondering, probably a little stupid question, but you know the little area
Uh-huh.
under the intersection?
Uh-huh.
Which part does that go to? Exactly.
Neither. You're talking about right here, right? That little triangle looking
Yeah,
shape?
goes to neither?
No, because look, the area between the curves, these are the curves. It's like an orange slice, right?
Yeah.
See this? And then over here, it's like just like a half a, you ever get French toast and they cut it in half?
But
That's what that is over here.
So you still don't, yeah, but you don't.
There's nothing going on there, no. Because they're intersecting. If two things are intersecting, is there any distance between them? So if I'm right next to the desk, what's the area between me and the desk? It's 0, because I'm standing up against the desk. When I spread out, there's more area between us, right? More volume, really, because it's three-dimensional, but theoretically area. Okay, so when they intersect, there is no area between them. They're just next to each other, or adjacent, if you will. All right, so Let's find the intersection point. This is the most important thing you're going to see right now, what I'm about to do. And so many students have a tendency to make a mistake on this one part. So I want the intersection. Tell me how to do the intersection. Good. Then I press. Number 5, intersect. Intersect first. We'll do integral in a minute. Oh, pressed it too many times. Okay, intersect. First curve, go over. I'm looking for the intersection. Remember, I just have to highlight the curve somewhere?
Yeah.
I'm not finding the roots. That's the roots, Kenny.
Yeah.
Second curve, enter. Guess, enter. Okay, there's my intersection. Awesome. Right? X equals 1.701561. Okay, what did I press again? Let's do it one more time. I press second, calculate. I press the number 5 for intersect. On the first curve, I have to move that little dot over until it gets near the intersection. Hit enter. Do it again, hit enter. Then it's going to say guess. You want to guess right there. Hit enter one more time. Okay? Now, I might want to write this number down. 1.701526. All right, so let's go ahead and write this down.
You have to write the whole thing.
Give me the decimals. Give me like 8 of them. 70.
15621.
Okay. So I'm going to have to write that down, right? It's a little bit annoying. Now, I also want to think maybe there's a way I can store this. So how can I get this answer and actually figure it out? And keep it in the calculator so I don't lose its memory.
Wasn't that alpha A or something? Yeah, it's alpha, whatever letter you want it to be.
So just press alpha A and hit enter?
I'm going to say alpha.
Alpha's the
That was
second.
just at the end of the summer. You plug in the function on the main screen, plug in that input.
What do I press?
Store.
Isn't that a store button? Okay, Mr. Smith told me this last night. He's like, try it out, see what happens. I had no idea about this. I had no clue you could do this. Hit store,
Oh, so it's not.
and it's storing the answer for x in a variable. Watch this. Second alpha A. Now the answer you got for the intersection is stored.
Mr.
What did I do wrong?
You didn't put alpha. You just put alpha math. Look.
There was no answer for it.
Mr. Smith.
Don't blame Mr. Smith.
He did tell me to try it first. I tried to make sure it still works on these calculators.
Wait, what do you mean?
Yeah, man.
Still works.
It's so annoying.
Let's try this.
Let's try another way. I have another idea. So we come up with a solution. Let's try another thing. Go to math.
We thought about it the wrong way.
Go to math. Let's find f intersect if there's a function. And I know there's f integrate. That's integrate. I think intersect is if we go over.
Yeah, we found out.
Whoa, whoa! I'm not pressing it anymore. Stop. Okay. Maybe int is intersect. Maybe that's what this is. Let's press intersect. Let's press y1, comma y2, and see what else we need there. And maybe there's a syntax error. So vars. Let's go over to y1. Enter, enter. Comma vars. Let's go over to y2. Enter. Down. Enter. Maybe comma x. Should I probably put comma x? Does really see that?
I did it with, like, I just picked a variable, and then, like, I think it's...
So tell me what to press.
Yeah, I don't think it's doing anything. I pressed quit, and then I got A and S, like, I got an answer, and then, like, all that other stuff. So it's like, it's stored.
Oh, interesting. Okay, that's a good way to do it. So we got to go to the home screen and press store. That's exactly what we got to do. Absolutely right. Can I try this though still?
Sure.
All right.
I'll go back.
Kind of excited. This might work. Did anybody try it yet or
Did
no?
you set your limits though?
That's what I'm wondering. That's exactly what I'm wondering. Do you have to give it? You got to give it limits actually. It needs a left and a guess. Let's hit enter and see what happens. All right, let's see. Okay, so maybe we need some limits. Let's try. What was the intersection again?
Negative, well, 1 point,
1 point something, right?
yeah, 1 point.
So I'm going to go from 0, comma 2 then, if that works.
So the function was 1.072.
Why does it give me an argument? It's so annoying. What if I just guess instead? Maybe I need to give it just one answer for the guess. Edgar, research, quick. The int function, int, on a T84, what are the arguments that it needs? How many inputs? How many functions? How many independent
We
variables?
should make sure that's actually.
Make sure it's intersect, actually.
Yeah, make sure it's intersect.
Edgar, we did math.
Or that's really-
We went over to number, and we went down to int. I think it is, Kenny.
Just try Christian's way.
Oh no, we're good. Absolutely. His way definitely works. He's right. And I know exactly what he's saying now. Did you go to the home screen, hit store, and it worked?
Yeah, I think, I tried to do it again, and
Just hit alpha A, enter, and see if it comes out, and you see if it works. Press alpha A, enter, and display.
But did she store it in like a big alpha?
yeah, it's just...
Oh, well then press it over there.
Yeah.
I'm pretty sure what you're saying worked, Christian.
Wait, did
I
I
don't
do
No,
something?
it did, because I showed you that I got 5 more than what it was.
Okay, so here, let me tell you what he was saying.
Yeah.
We did it at once.
While Edgar's researching, let's go to our graph, sorry. Let's do the intersect again. Second, calculate, hit the number 5. It should be flashing there already, enter, enter, enter. Okay, now, right now, the computer or the calculator is thinking about this number. That's what we're saying, right, Christian? So this is its answer. So let's go to the home screen now. Second, quit. Okay, clear what's here, sorry. If you have anything there, say clear. Let's press store and just press A now. And it should store that in A. Was it 1.70?
Yeah.
So now it's stored in A. That's exactly it. Awesome job, Christian. Thank you. Okay, and that's probably what this meant actually. What do you mean that? I wonder. Okay, I gotta ask him. So now that we have it stored in A, now I want to know the integral from the -4 to A, right?
Yeah.
Well, what was it again? y2 minus y1 or y1 minus y2? y2 minus y1. That was this one right here. y2 minus y1 from -4 to A, because we stored it as A in our calculator, right? 1.7007, whatever. That'll give us the green area. Let's do that first. So let's go back to our calculator. Let's either go to the graph and do it, but that's too much work, because then I have to do one integral and the other. I can't do that on the graph. So let's use the integration function. Let's go to math. Let's go down to number 9, I think it was, or just hit 9 if you know the number. It is 9. Hit 9. Now we need to do y2 minus y1, right?
Yeah.
Again, y2 is the upper function, y1 is the lower function. So y2 minus y1. Go to vars, over to vars, function, hit y2, hit enter, then hit minus, go to vars, over to y vars, enter, go down, hit enter on y2, comma.
Oh, you won Y2, Y1.
Dang, I went to y2 twice. Awesome, guys, you're picking up. I know, that sounds stupid, but it's the truth. It means now you really know what I'm saying. Because there are times I make mistakes and I realize it, and sometimes no one else does.
Half of it just go out like.
Well, now you're all
We're out,
here.
we're out of it sometimes.
Now we're all here. y2 minus y1. What did we say yesterday or the other day when we did this? What has to come next?
Plus B.
The X and the
Yeah.
X in the domain, was that right? X in domain? Okay, if that doesn't work, then it's domain, then X. You could always check either way.
I think X came.
What was my domain again? -4 to the answer we stored in A, right?
Yeah.
So -4, comma, alpha A. Close parentheses, enter.
Just to make
It's
sure.
like, I
We
mean,
did
we're
all
singing
that,
like,
we
you
did
know,
all that.
angels singing right now, yeah.
Just to make sure we're right.
That's that one area we just got, that's the green area.
Just to make sure we should like put it back.
To make sure, we should find the integral of y2 by itself in the graph, then find the integral of y1 and subtract them, and we'll get this exact number. Absolutely. Now, but I don't want just that, right?
New method.
I want that plus the next area, don't I?
It's a story.
And we said the next area, doesn't it switch? Isn't it y1 minus y2? And it's from A, or alpha A, all the way to 4 now?
Second.
So, you know what? Don't do that. Here's what you do. I'm going to press second enter to bring that up again. And then I'm going to press plus and do another FINT next to it. Do it all in one line of code. Let's go to math. Let's go to number 9 again. And we'll do another integral. But now we're switching up our integrals. So what is it going to be?
We should have stored it actually. Put it back in there.
But Kenny, I'm showing you that we never had to do it in the first place. We shouldn't have done the one line by itself. We should really do it all online. So now we're doing y1 minus
Can't argue, that's the problem.
y2, comma, x, very good. Now where are we going from now? A, the intersection, to 4.
You didn't memorize the numbers.
And look at that. That's the area of those two regions. Now, on the AP exam, if they give you functions that are exponential growth, or ones that might be tough to find the intersection for, that are not, you know, just whole numbers, or numbers like 1.5, easily roundable numbers, or easily represented numbers as decimals, like 3/2, then there's a chance they're going to have you use your calculator. It happens a lot. It happens a lot when you're looking at the graph when it's exponential or sinusoidal. Because sine curve, there could be many intersections. Let's look at an example of that now. All graphically we'll do it, okay? So let's say our function is now sine of x. Okay, that's the numerator. Let's make sure our mode is in radians. Our mode is in radians. The greatest integer function is a step function that always rounds up to the next integer.
That's
Or,
what you give me.
yes. So greatest integer function, for example, Oh, really? That makes sense. That's what I said yesterday. I was talking about piecewise. It's a step function that looks like this. It's a greatest integer function. So if the integer, if the number you're looking at is 4.2, it always rounds up.
Yeah.
Okay? It always rounds up. Least integer, which is like a, so it's a ceiling function and a floor function. Remember these terms? A ceiling function is when it rounds up to the next integer. A floor function is when it rounds down to the next integer. And there are always going to be steps along the way. Because it's always rounding to an integer. It's never going to be a decimal y value. Okay? So if the number is like 2.1 along the x-axis, if it's 2.1 right here, it rounds down to 2 for a floor function. So anything that's a decimal, if you rounded a decimal down, what would it round to? Like 0.5 rounded down, what does it round to?
0.
What does 0.8 rounded down round to? Down. Down. 0. I'm telling you, turn around. 0.9 rounded down. Still 0. So any of these decimals rounded down are all 0. What about a number like 1.5 rounded down? What does it round to? And isn't this the x value 1.5? So the y value here is always 1. The next one, anything in the 2 range, is going to round down to 2. So what kind of a function are we going to get? We're going to get a step function.
We say he's down, like, no matter how high the interval is.
So pick an x value here, pick an x value here, here, here. That's what a integer function is. And that's probably what that is on the calculator. So let's use Christian's method. I would agree with it once we figured it out. He told us, okay, the intersection that you get on the graph, go back to the home screen, and then just hit store answer, because it thinks of the intersection as the last answer, and it will store that in alphabet. We'll do that again for this example. Thank you. Edgar, and this is good to know, guys. These are functions that are used wide, especially if you study any engineering functions whatsoever, it's there. All right, so let's go back to our y2. What did I make y2? Let's think about this for a second now, please. Let's think. A sine curve ranges from what to what? 0 to 2 pi is the domain. What's the range?
1 and
-1. 1 and -1. Remember, it goes up to 1 and down to -1. Up to 1, down to -1. Okay, that's the what again? Amplitude, 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 amplitude. Okay, wavelength is the length of one wave. The frequency is how many waves are every 2 pi cycles, or every 2 pi distances. Okay? All right, so let's make this a little bit taller. So what should I put in front?
2.
A little bit more than that.
5, 4,
5.
6, 10, 20, 5.
Let's say
32.
15. Ah, nice. 15. Okay? So clearly 15 is going to go off our graph. That's fine. I did this on purpose so that you know it. Sometimes reset your window. Then let's also look at a graph like...
A linear function, just crosses everything.
I got Billy all these.
Horizontal.
What linear function is it?
Let's say a linear function.
Exponential.
Give me a
It crosses everything.
negative y-intercept and a positive slope. Give me a linear function. It starts down here and it increases. Negative y-intercepts and a positive slope. Effect. Negative y-intercept, positive slope for a linear. What do you think? Give me a slope. Some positive number for a slope. What do you want to pick here? Any number. How many x? 2x? 4x. Okay, perfect. 4x. Now give me a negative number for the slope, or for the y-intercept. Sorry, see, I'm confusing myself.
Put his base up there. Oh, suppose we're going to put your base up there.
Negative 18, perfect. All right, I'm glad you picked these numbers. Let's think about why. First of all, negative 18 is going to cause me to have to lower... No, that's not an error. It's because I put a minus sign first, a negative sign first. I fixed it. So we want to graph this, and this is a great example because negative 18 will cause me to go all the way down there, and then the 15 will cause me to go all the way up top. Okay, so it's a really good example. Look at my line. See it cutting across here? There's our line cutting across. So let's go to my window, and let's go from negative 20 to 20 in the y. Okay, negative 20 to 20 in the y. Now let's pick a range we want to find the actual area between. Let's look at the graph first, though. There's my sine curve, and boom, there's my other curve. Okay, good choice with the 4 and negative 18. I think it works. Now, let's find the area between the curves from here, which is, or no, you guys pick. Pick something to the right of the y-axis, because we're going to have to go down further. 10? Okay, well 10 is here. I want a starting point over here. 2 pi? Okay, 2 pi, that's fine. That's our starting point is 2 pi, which is around 6.28. So over here somewhere, okay, which is happens to be what?
Exactly.
The root. It's a sine curve, right? Sine of 2 pi is 0. That's why that's right there. Okay, let's go from there. Or let's make that our upper limit, Edgar. Make that our upper. And now everybody else, somebody else pick a number here. In terms of pi also, between 0 and 3. 7 pi over 12. Perfect, that's fine. Okay, so we'll do an integral from 7 pi over 12. So let's go to our x-axis to see what we have here. 7 pi over 12 all the way to 2 pi. That works for me. I'm going to hit graph. And notice, why am I graphing it, guys? Why am I not just saying, I can do this myself? What am I looking for again? Intersections. That's why I'm graphing these. If the functions are very simple functions, and there may be 2 linear functions, or another quadratic with another quadratic, or even a cubic, you can find the roots of a cubic using that table. It's not hard. Okay, so you could do those by hand. But here, let's find our intersection. So,
and so that area between the 2 intersections is all...
let's do it again. Let's break it up. Okay? Somebody tell me on the left side of the intersection, what will my area be in terms of the integral? Integral from what to what of what function minus what function?
Wait, which one?
Look what they are. They're up here. They're up here. You can see where they are.
y1.
Think about it first. Give yourself a second one. Think about which one here. We're going to do what minus what here in this region. From where to where, giving some sort of bound or limits. Have ideas?
Yeah.
Okay. Somebody want to volunteer now? Somebody want to volunteer now for this one meeting? What do I? And we can step ourselves through it together. I think we should do that. So, Rosie, tell me. I'll step you through it. We'll work on this. What's the upper function going to be? Which one is the upper function? y1, perfect. Which one's the lower function? y2. So I'm integrating what minus what, Rosie? Very good. Upper minus lower. What do I put at the end, really? Good, dx. Now, Rosie, what did we start at? What was this value again? Do you remember? Did you write it down? What was this x-coordinate that we're starting at and going toward? You remember what he said as a number? 7 pi over 12. So I started 7 pi over 12, right? Because that's what I'm starting from. Now, Rosie, what can I call this? Rosie. C, right? That's an intersection, C. Now, if I'm going to store it, what am I going to store it in probably? A or B or C, whatever. You want to call it C? Let's use C as our dummy variable. Capital C, because I'm storing it in capital C on this. Perfect, well done. Okay, and what does that tell me? That tells me this area right here. Now, on the other side, Jasmine, help me with this side here. From here to here, what do we got? Awesome. Good, and what was the last? What do we pick again? 2 pi, yeah. Again, 6.28, that's what Edgar chose. Awesome job. And there's our area in there. Okay? So again, we're doing the same thing. Let's go to our home screen. Let's use the same function we just had stored. Press second enter. And we'll go y1 minus y2, y2 minus y1, and we have to find the intersection. So, let's do this. Clear. Good. Let's go to second intersect. Or second calc, sorry. Intersect. First curve, let's go over to the intersection. We'll be good once we get near it. I went too far, clearly. Enter, enter, enter. There's our intersection. Go to your home screen. Second quit. Press store right away. Press alpha C. We're storing it in C. Doesn't matter what we call it. Hit enter. There's our intersection. Now I want to call this one back up, don't I? And I'll reuse this because it's already there. I'll just type over. So maybe I'll just press second enter, and it brings up the last second command. It always brings up your last entries. I'll go up here, and we had y1 minus y2. So I'm going to change this one. I'm going to press delete, delete. I'm going to insert a minus y2 in here. Okay, we're going to do y1 minus y2. See how I'm trying to do it quickly? I'm going to go over to y bars. Bless you. y2. Now I've inserted y1 minus y2 from x. From where to where again? What was our first one, Christian? Good, so I'm going to press, watch, delete, delete. Then I'm going to insert the number before it. So I'm going to press second insert, 7, second pi divided by 12, then my comma. Now I'm not going to A anymore. Where am I going now? C, alpha C. Then I want the integral of y2 minus y1. So I'll delete the y1 from here, leave the y2. Second insert, go to vars, over to y vars, enter, enter. Oops, I forgot my minus clearly. Second insert, I need a minus in there. So now it's y2 minus y1 on x from the intersection, which is C, all the way to what was the final limit? 2 pi. 2 second pi, close parentheses. Okay? And again, this is exactly what we wrote a second ago, and now it's in our home screen. We press enter, we get 55.88. Okay? Now again, the question might ask you this. If they ask you to find the area of this one, and then they say find the area of this one, and then they maybe for some reason ask you to add them, which I don't think it would, you'd have to do them in pieces. You can't do it all together, right? You'd have to do the first integral, which is up to here. That's the first integral, get that number, and then do the second one. I don't think they would ever do that. Usually they ask for a range where there's intersections. What if there's more than one intersection? You're going to need more than one intersect answers. You have to do a few storages. We'll try and do that one on Monday, okay? Or rather Tuesday, because we'll work on Monday. What I do want to do is give you some practice problems now. So I want to give you some problems as above. Christian?
Why is it that we're using addition in the calculator when you want to just put it on paper?
No. You're using subtraction for each area, but we're adding those two pieces together.
Okay.
That's where the addition comes in. You're still using, it's always upper function minus lower function, always. Always.
Okay.
Okay, but when you're adding two pieces, that's where the plus comes in. It's a good question. I can see where there's confusion. Come on.
Yeah, I was separated, so when I did it, instead of adding the integrals and function, I subtracted it, because I thought that you're not supposed to subtract.
Yeah, it's times 2, but you already do that with
Yeah.
y1 and y2. But
All right, here we go.
What was weird was he was saying that you don't add them together, but don't you just add them there? You added both of them together.
So,
He's talking about you don't add multiple intersections.
what's the process? All right.
Now you know why in middle school they don't want you to use it.
The textbook problems, to give you a little bit of a heads up, the textbook problems don't give you upper and lower limit to go from. They don't give you A to B. You know what they say? They say find the area between the two curves. So here's your examples. I'm going to give you some problems right now. Okay, to work on over the weekend. Okay, and let me explain before you go anywhere. Try numbers, page 396. This is section 7.2, page 396, exercises 15 through 25. No, it's too many. Let's try 15 through 22. Now, let me just quickly give you an example of what I'm talking about. They do not give you lower and upper limits, but they give you functions in a way that one is like a parabola like this, and one is a parabola like this. And it'll say, find the area between the curves. Okay, between the curves. They consider this the area between the curves when they're doing it like that. Just to give you a little preview of this book. It's a little bit different than the way I would have done it. So when they say find the area between the curves, they're talking about that area. Even though I know this is still the area between the curves, and we've done it that way. So practice those. Take a look at the graph. Use your graphing calculator. Try and also check it analytically. Okay? So try and do the integrals by hand, but check on your calculator first.
Wait, does left intersection matter?
Does the left intersection matter? They're saying find the area between these two curves, not giving you limits, considering each of the intersections, the starting and ending.
And they give you functions, right?
Okay? Yeah, so they give you functions like 7 minus 2x squared, and then x squared plus 4. That would be a perfect example here. You know, this would be shifted up, but it would still be the same idea. Okay? I might post a video for you guys to watch, maybe like a 10-minute video on something, just a good example of this, a good example to reinforce it. Well, we'll pick up with this on Tuesday. We're going to keep going with area between curves to make the examples a little bit tougher so we're ready for the AP exam.